So to continue, we looked at the composition of the atmosphere. We looked at the vertical structure of the atmosphere, one of the very important concepts that you must remember. What comes next? Slowly we'll build how circulation happens and how atmosphere and ocean begin to move energy. The simplest concepts often are just around you. In the tropics, we don't have these kinds of heaters, but you have air conditioning and so on, or a fan moving air around in your room. But this is a very important concept again to understand. As I said, tropospheric temperature is warmest at the surface and decreases with height. And we said it's because greenhouse gas is warming the surface and the atmosphere is heating from below. What happens when it is heated from below? So if you have a radiator in the corner of a room which is emitting heat, the air that's in touch with this radiator is going to get warmer and it's going to rise. It's going to hit the ceiling just like our tropopause, and it has to move away from along the ceiling, away from the rising air, right? This advection of heat by warmed air molecules is called convection. How is it different than other concepts you have learned? You have probably learned conduction by now, where if you have a metal piece, for example, if you heat it on one end, slowly the temperature would increase to begin to increase towards the other end. What's happening there? Molecules, by vibrating because of increased temperature and kinetic energy, are transferring the energy along the metal bar to the other end. That's conduction. In the ocean and the atmosphere, conduction is basically completely negligible. We don't have to worry about it at all. But convection is very important, where heat is physically being moved by molecules themselves, taking that energy and going away and giving it up elsewhere. Okay? So convection in that sense is a very important process in the atmosphere. All this monsoon rain we get, this is convection. Water vapor is basically picking up energy from the ocean, is moving into the atmosphere, forming clouds, coming somewhere, and that energy is being released, condensation, heating, rainfall is happening. This is convection, right? So air, as it goes away from the heater, convector, cools down and sinks, or it hits the wall and sinks, or there is a window that's bringing in colder air by some other process like diffusion and cooling the air, and then that air is going to come back towards the hot radiator and rise again. So you have set up this convection cell which is beginning to move the energy. This is exactly what's happening in the atmosphere as well. Water vapor in the air is a critical component of this energy balance, and we'll see it's a very non-linear process, which makes for very difficult processes to understand, but very interesting and beautiful solutions as well. So water vapor is obviously dependent on air temperature. I think you have a very good intuitive sense that warm air will hold more moisture. Cold air will typically hold much less moisture, depends on the pressure as well, but nonetheless, as you go to colder places, air typically tends to be drier. Your skin gets drier, you need moisturizer, whereas in the tropics, warm air always feels humid, right? So that's something to remember. So water vapor in the air also influences the density of the air. Moist air is lighter than dry air. Just the fact that water vapor is lighter than dry air. So when you mix them, you produce lighter air. Atmospheric pressure, there is a relation called hydrostatic relation, which is related to various concepts that we haven't introduced yet, but essentially the thickness of the air column above you determines the surface pressure. We have evolved to live at the surface. We fly around as well, but we are carrying the load of the atmosphere above us, right? We are used to it, but you can imagine a little fish living in the ocean. Water is much heavier, pressure is much higher in the ocean, but the fish is evolved to live with it. But you can remember a very good example. If you take a fish from a deep ocean to the surface, the pressure changes so much, reduces so much that it can explode, right? Because its lungs are used to high pressure. If you reduce the pressure, the lungs will explode. So the pressure in the atmosphere depends on the thickness of the air column above. Okay, this is important because as you go above a mountain, the air column is far smaller, so the pressure is lower. That's why it becomes harder to boil water and so on, which we will see later on. Okay, so thin column of air means lower surface pressure. Cool, dense air sinks, okay, because its density will be higher and it will sink. Its buoyancy becomes lowered, so it sinks. Warm, moist air rises, and as we said, the pressure is lower with height, so any air that rises into a lower pressure is going to expand. If it's moist air, when it expands, it cools, which means moisture is going to condense, right? These are the kind of processes we are adding one by one, but they're all simple, so just keep following them and understanding them to be sure to be able to pull them together every time. So air obviously moves from high pressure to low pressure, right? So this is showing here warm air. It's also saying low pressure, and it's showing that the molecules of air are farther from each other. They're free to move around because temperature is higher, kinetic energy is higher, and so on. And the air is rising here. Why? Because warm air has got lower density than the air above, so it rises, and there is a low pressure near the surface when you have warm air, right? Warm temperatures make the pressure lower. If the air rises, that air is replaced by air that's coming in horizontally. This is called convergence, becomes very critical. So warm air rising, convergence happening to fill in the gap, mass balance, and the warm air that's rising, if it rises all the way to the, let's say, tropopause, or to the level where it loses its buoyancy, becomes neutrally buoyant. If it hits the tropopause, it has to go away because we said tropopause is like a ceiling. Remember the radiator we looked at where you hit the ceiling and then you have to follow the ceiling. So air is flowing along the ceiling. Eventually it cools down as it goes away from the warm rising air and keeps losing its temperature to the neighboring atmosphere, becomes heavy enough at some points and gets less buoyant and begins to sink. The sinking air actually compresses and warms up a little, but nonetheless sinking air creates high pressure. So the air is moving away from this high pressure region, which means sinking air is replacing the air that's moving away, or sinking air is going to push the air away from where it's sinking. So the molecules are closer together here because of colder temperatures, lower kinetic energy, and so on. So this is a simple figure, but it shows you in a simple sense how the circulation in the atmosphere can get set up. The tropics have warm air, low pressure, rising air hitting the ceiling, let's say moving towards the poles by hitting the tropopause, getting colder, sinking somewhere at the higher latitudes, creating a higher pressure, and diverging from the high pressure and converging towards the low pressure. This is our first simple circulation. This happens in the real world at a large